In this question, we consider the charge associated to the global phase symmetry of the theory. So that's the Lagrangian, and it's obviously invariant under the following transformation. So where phi is just a global phase, and okay, so phi star E minus I phi. Yeah, the theory is invariant under this transformation. Therefore, we have an associated charge, which is given as the special integral of, okay, there's this factor, phi star, pi star, minus pi phi. So, in order to evaluate that, we can just use the expression that we had in the previous questions for phi and pi in terms of A and B. So I'll just write directly what we get. So that. So we have two momenta integrals. Okay, and then we have this factor 1 over I over 2. And then we have these two terms, so I'll actually start here. So the first term is just WQ omega P, it's factor minus I, and we have the operators here, B minus P. So in order to see that, you really need to just really use what we had in the previous questions. P prime or Q, okay. Q here, minus B minus Q, okay, exponential P minus Q x. And the second term, which is pi phi, is minus omega P for omega Q. There's a factor I, and AP dagger minus B minus P, there's a minus here, A Q plus B minus Q dagger exponential I P minus Q of x. So as in the previous question, we perform the x integral, and this will give us a factor 2 pi cube delta P minus Q. Okay, so I'll do that directly. So we are left with this P integral. Okay, so all these factors vanish, and we are left with this I over 2. Okay, I will extract minus I, there's a factor 1/2, and then we are left with these operators, B minus P, AP minus B minus P, minus, or plus rather, AP dagger minus B minus P, AP plus B minus P dagger. And that's just one. And we need, as previously, to simplify these operators. So we have 1/4 here. And so what we have here is, so first AP, so we have two factors, so you see the first two factors here are the same. So I'll just write that, AP dagger AP, so that's 2. And okay, we have minus 2B, so it's minus P, B dagger minus P, but I can make a change of variable and have B, P, BP dagger. and the cross term, they just vanish as well. Okay, because the operator commute. So that's not a problem here. We now, so we have this expression, and as before, we can, so 1/2. So as we did, so I will just write that. But for the second term, as we did in the previous question, there's actually here a constant term, which is very large and infinite, but which we may neglect, or at least not consider it for physical purposes. So our result is that, the result of, so that's the expression of the charge in terms of the annihilation and creation operators of the A and B particles. So in order to see what's the charge of the particles, we can compute the commutators. So Q A, let's say Q dagger, so that's quite easy to compute. The integral can get out of the commutator 1/2, and we have here simply AP commutator AQ dagger. Now AP dagger and AQ commute, so actually this can go out of the integral as well, and therefore we are just left with so 1/2 of a Q dagger. Okay, so that's the first result. The reason for that, of course, is that AP AQ dagger is equal to 2 pi cube delta P minus Q. Okay, so this we have. And similarly, we can compute QB for a given moment mod Q, momenta Q, and we see that it's basically the same, except that we have this minus sign. So it's minus 1/2 BQ. So those are the results. So this means that the A particle, so the as here charge plus 1/2, while the particle that is created by the creation operator B dagger has minus 1/2 charge. So in the previous question, we've seen that both particles, so the one created by A dagger and B dagger, have first of all the same mass. They contribute similarly to the Hamiltonian, and now we see the difference between them. They have a opposite charge with respect to this symmetry transformation here. So we can really interpret them as A, so since positive, we can say that's the particle, and B is the antiparticle.